In this video, we are going to understand how a basic transportation problem can be formulated by using linear optimization methods, okay? Linear programming formulations, mainly. So in this transportation problem, we do have three plants. We do have a plant in Marietta, Minneapolis. Sorry, two plants. We do have one plant in Marietta and one plant in Minneapolis. And we do have four distribution centers, one in Cleveland, one in Baltimore, one in Chicago, and one in Phoenix. Our problem is to figure out how much to ship from each of these plants to each of these distribution centers. What you see here is that these are the unit costs for shipping one unit of item, whatever that item is you're shipping, from Marietta to Cleveland, Baltimore, Chicago, and Phoenix, and from Minneapolis to Cleveland, Baltimore, Chicago, and Phoenix. So for Marietta, your capacity is limited. You can ship at most 1,200 units of that product. And from Minneapolis, your capacity is a lot less. It is 800 units. Cleveland requires 150, Baltimore requires 350, Chicago requires 500, and Phoenix requires 1,000 of units. So the optimal, well, the problem is at minimum cost, what should be the amount that I'm shipping out from each of my plant to these distribution centers in such a way that the demands are satisfied, okay, and then the capacities are not exceeded. Well, this is the simple transportation problem. So let's make an index for each of these plants and DCs so that we can draw the network representation of them. So let's call these plant I's, 1, 2 distribution centers, 1, 2, 3, and 4. Okay, so these are my plants 1, 2, and these are my distribution centers. Okay, I do have 4, 1, 2, 3, and 4. Okay, in each of these you can ship goods to each of these, right? Okay, this is the network representation of these transportation problems. So what you put on these arcs, so you put the cost, the unit cost. So from Marietta it is to Cleveland it is 1260, right? It's 1260. From Marietta to Baltimore it is 1435. 1152. Okay, and 1758. Similarly, you can do the same thing from the second plant to all the DCs. The capacities here we have in our plants 1200 and 800. On the other hand, the demands from our distribution centers are 150, 350, 500, and 1000. Well, as you can see, if you add these capacities up, that is 2000. If you add these demands up, that is also 2000 as well, right? That's called balanced transportation problem. Okay, why these are balanced? Because the total amount that we have is equal to the total demand from distribution centers. So if that's the case, then this is a balanced transportation problem. What happens if one is strictly less than or greater than another? So then you have an imbalanced transportation problem. In that case, you have to do a formulation trick to be able to find this optimal solution. Okay, so this is the network representation of the transportation problem, and these are the data that we have originally. So the problem is, what should be the amount of shipments from each plant to DC so that the DC's demands are satisfied, and then we are not exceeding the capacities that we have at the plant. So again, the first step is to define the decision variables. So here I just already gave you the hint. The decision variables are the number of units sent from plant I to distribution center J. So here we used set notation. So set I, this is set, okay? set I. Those are a set of plants. And set J, set of DCs. Okay, and then for I, we index on little I. We do only have two plants, and for J, we do have 4 plants. Okay, Xij is then going to give us the number of units sent from plant I to distribution center J. Which I to which J? Well, if this is, for example, x12, means that it is from plant 1 to distribution center 2. Okay, and already defined which those are. The objective function, well, the second stage of defining a linear optimization model is to create the objective function, right? The objective function is to minimize the total cost. The question is whether that function that you have here is the total cost. These values, 1260, 1435, 1152, these are the cost values that are grabbed from this table, right? And more specifically, this 1260 times x11, again, by definition, it is the number of units sent from plant 1 to distribution center 1, right? And this 1260 is the unit cost for sending 1 unit of good from plant 1 to distribution center 1. So again, if you do the same thing for all other plant and distribution center combinations and add them together, yes, you can get actually the total cost function for this transportation problem. And we would like to minimize this function for sure. Okay, that's a check. Remember, we do have several constraints, so for each plant, we have to make sure that we are not exceeding our capacity. So let's check out whether that's the case for the first plant, right? So x11 is the amount shipped from plant 1 to distribution center 1. x12, the amount shipped from plant 1 to distribution center 2, from plant 1 to distribution center 3, and then finally from plant 1 to distribution center 4, right? This whole left-hand side gives us total amount shipped from plant 1. Well, that's the case. If that's the case, then we can make this less than or equal to the capacity. Well, perfect. This constraint helps us enforce the fact that the total amount shipped from plant 1 cannot exceed 1200. Well, we are going to do the same thing for plant 2, right? The only thing we are changing here is the index, the first index, in order to represent this constraint for plant 2. Okay? For each distribution center, we have to have one for the demand restrictions, right? So this is distribution center 2, distribution center 3, and distribution center 4. Okay. For each distribution center, we have to make sure that the total amount that that specific distribution center is getting from plant 1 and plant 2 should be exactly equal to, or at least the demand value that they are requesting. So x11, again, by definition, it is the number of units sent from plant 1 to distribution center 1, and x21 is the amount of goods sent from plant 2 to distribution center 1. So if you add them together, there is no other plant, right? So we do only have 2 plants. If you add them together, you would get yourself the total amount shipped to distribution center 1 from those 2 plants. And you are just going to do the same thing for the other distribution centers. Again, the only thing that's changing here is the second index reserved for distribution centers, right? So this is for the third one, and this is for the fourth one. And you have to have a function that says that these values, the total amount shipped to these distribution centers, are exactly equal to whatever they are requesting from you. These symbols can be also greater than or equal to. It's not going to change anything, but I prefer to use equalities here. Again, finally, we have to add these greater than or equal to restrictions because we cannot ship negative amount of goods, right? So it doesn't make sense. Okay, what's the optimal solution? Again, we don't know, but we can use Excel solver to answer that question. Here I reserve these cells this time for my decisions, right? So basically these yellow cells are going to give me how much I'm going to ship from Marietta to each of these distribution centers and Minneapolis to each of these distribution centers. In order to keep track of total shipped, I just sum these cells up here for Marietta and for Minneapolis, and how much to keep track of shipped to each distribution center. I just sum these columns up so that it can give me a value. I can make them equal to their demands and also their capacities. The total cost, on the other hand, is going to be the sum product of these cells, these cost cells, with these decision variables. Okay, if you go to solver, data, solver, I already added these constraints in, so the objective function is to minimize this cost right there. It is B19 by changing which cells, these cells, decision variable cells. My constraints are B16, E16, B16, right there, E16. The demand values for each distribution cells must be equal to whatever I specify here. Well, okay, let's do this together in order to prevent any confusion. So here I have to make sure that whatever I send to my distribution centers must be equal to whatever they request, and whatever I'm shipping out of my plants should be less than or equal to my capacities. Okay, so what I just did here with just single selection of those two right here, total shipped, I actually added two extra constraints at a time because they share the same symbol. Yes, you can do that. And then that's about it, I guess. Yes, and if you click, so make sure that your constraint variables are non-negative, then solve this problem. Solver found a solution, all constraints optimal conditions are satisfied, click OK. At the optimal solution from Marietta, you can ship to Baltimore and Phoenix with these values, and from Minneapolis, you can ship to Cleveland, Chicago, and Phoenix. Okay, that's your optimal solution. And then you would be having a whole cost of $28,171. That's pretty cool.